Hello everyone, I am Pugazhendhi.
Hello everyone, I'm Subhadip, and in this short video we are going to discuss about our recent work, possible new neutrino source class 3 sigma detection of high energy neutrinos from supermassive black hole binary candidates. This work has been done with Rachana under the supervision of Zhou and Ranjan Laha. So one of the biggest questions in physics is which are the sources of cosmic rays and the acceleration mechanism behind it. Cosmic rays are charged nuclei which are bombarding our Earth from every direction of the sky. These cosmic rays are charged particles, so they get deflected in the intergalactic or extragalactic magnetic field while reaching to us. So using these particles, we cannot trace back their origin. But these particles can interact with matter or radiation inside or near a source to produce neutrinos and gamma rays. These gamma rays also travel in straight paths, but the problem is that if gamma rays are very high energetic, they interact with CMB photons to produce electron-positron pairs. So the signal can get attenuated. On the other hand, the neutrinos are chargeless and they only participate in weak interaction. So they can reach us undeflected and can tell us where are the cosmic reproduction factories. So the idea here is to understand these neutrinos to know about these cosmic reproduction factories. We have a fantastic neutrino telescope called IceCube, which is located at Antarctica, and IceCube has observed high energy neutrinos coming from every direction of the sky. But the astrophysical sources which are actually contributing to these high energy neutrinos remain a mystery. Recently, IceCube has reported that X-ray bright Seyfert galaxies can be a potential source class for these high energy neutrinos. So in this figure, the x-axis is the energy in GeV, the y-axis is the energy flux in TeV per centimeter square per second. The orange band here represents the diffuse astrophysical neutrino flux measurement by IceCube. The blue and red bands here represent the energy flux measurement of these four Seyfert galaxies. Here you can see that these four can only contribute a tiny fraction of the total diffuse flux measurement. Also, there are several classes of sources that have been searched in the literature as a potential candidates for these high energy neutrinos, such as gamma ray burst, galactic X-ray binaries, AGNs, pulsars, etc., etc. But none of these classes of sources can actually explain the 100% of the total diffuse astrophysical neutrino flux. So the question is remaining, what are the other classes of sources that are actually producing these high energy neutrinos? So in this work, we want to ask a question, what if supermassive black hole binary systems are actually producing these high energy neutrinos? So we all know that a supermassive black hole binary is a system of two supermassive black holes orbiting each other at the center of a merging galaxy pair. And this paper by Jarosky et al., the authors have shown that supermassive black hole binary systems can indeed produce high energy neutrinos. And these neutrinos can be detected by neutrino telescopes such as IceCube. To test this idea that supermassive black hole binary candidates are actually producing these neutrinos or not, we have constructed a catalog of 693 potential sources using this reference by D'Orazio and Maria Charisi. So now let's move to the core idea of our paper and the key results. So we have done a likelihood analysis. So likelihood is nothing but a combination of signal PDF and background PDF, which looks like this. And we have added up the log likelihood for each of the sources and maximize it to find the test statistic, which is nothing but a logarithmic ratio of two hypotheses. One hypothesis here, it is saying that the neutrinos are coming from the supermassive black hole binary system. The other hypothesis is saying that everything is a background. Here the NS is the expected number of neutrinos coming from supermassive black hole binaries.
Now, using this framework, we conducted the stacking analysis, which combines the contribution of these individually weak sources to enhance the collective signal that can be detected by the IceCube neutrino. And these contributions can be weighted by different weighting schemes. And in our analysis, we conducted three kind of weighting schemes. The first is the neutrino flux weighting scheme, which is motivated by the Jarosky et al.'s paper on theoretical modeling of the neutrino emission from these SMBHB systems. And the next one is the bolometric flux weighting scheme, which makes the weighting factor proportional to the L bolometric by DL square. And the last one is the uniform weighting scheme, where all the sources contribute equally to the neutrino emission. And we have three kind of catalogs in our paper. First is the whole catalog, which consists of the 693 sources. And then the next one is the association-free catalog, in which we exclude the sources which are close to the previously known sources, like the NGC1068, NGC4151, etc. And the last one is the nanograv catalog, which consists of a small subset of 104 sources from this whole catalog. This we take from the overlapping or the common sources between our whole catalog and the targeted searches of for these SMBHB systems from the nanograv telescopes. And we conduct two kind of analysis. One is the spatial focus analysis, in which we only take into account the spatial correlation between the neutrinos detected by the IceCube and the SMBHB candidates. And the next one is the spatial energy combined analysis, in which we include both the spatial correlation as well as the energy spectrum of the neutrinos. And next, I would like to briefly explain regarding the key results of our paper by explaining the figures in our paper. First, I would like to start with our neutrino flux weighting scheme, which as can be seen in this figure. In this figure, the left one shows the energy weighted flux at 100 TeV in GeV per centimeter square per second per steradian, and the y-axis shows the log likelihood values. As mentioned, we have two kind of analysis. The red curve shows the spatial energy analysis, and the blue curve shows the spatial focus analysis. And the three catalogs are shown by three different line styles. The solid lines represents the whole catalog, the dashed lines represent the association-free catalog, and the dash dotted lines represent the nanograv catalog. I'd like to get the viewer's attention to this maximum likelihood values, that is the test statistics, is around 10.2 for the spatial energy analysis and is around 9 for the spatial focus analysis. This corresponds to a significance of around 3 sigma. And the right figure shows the energy weighted flux in GeV per centimeter square per second per steradian, and as a function of the energy of the neutrinos in GeV for the best fit spectrum that is that we got from our analysis. And we also show the total astrophysical neutrino flux measurements from the IceCube just for comparison. Now, similarly, we have done analysis for the bolometric flux as well as the uniform weighting schemes, and all the results of these three weighting schemes can be summarized in this paper. As the table. Now, I would like to get viewers' attention again to this particular weighting scheme, the neutrino flux weighting scheme, which shows a significance of around 3 sigma in the spatial focus analysis and a significance of around 2.5 sigma in the spatial energy analysis. Now, I would like to highlight that the significance remains consistent across all the three nested catalogs, indicating that our results are not contaminated by the previously known sources and the observed correlations are robust. Next, in conclusion, I would also like to note that the 3 sigma excess obtained in the neutrino flux weighting scheme hints at a possible neutrino emission from these SMBHB candidates. With future IceCube data, we can set a more stringent constraints on the contribution of these SMBHB candidates on the neutrino emission on the high energy neutrino scale. Now you can search our paper in the Google with the author's name or from the title, and feel free to contact any of the authors in case you have any questions. Thank you.